So I hope you're all enjoying yourselves today. I have been enjoying myself today. There were many fun talks by very excellent speakers. Thank you to be here, everyone. You're all here to learn more about Splatty, our fun splatting viewer that is going to revolutionize your view on a lot of stuff. I hope that you're going to learn about Gaussian splatting. I hope that you're going to learn about new C++ features that you never thought you would use on this kind of project. But we'll see. I don't want to spoil myself. This is the only slide that I didn't know what to say first because I'm too excited. So I'm going to start with CppNorth. It's so great. Please, a big round of applause to the organizers, the volunteers. It's been so great right now. Thanks, Mike. Such a blessing to be here. And the view is so beautiful. It's incredible. People on YouTube can't see it, but it's quite crazy. So without further ado, let's go and meet Splatty, our co-host for today's Splatty? No, it's supposed to be there somewhere. No. Wait, did you see something? No, it was supposed to be there. No, not this one. It's not supposed to be doing this one. Wait. It's supposed to be panning from the back to the front. And no, not this side, Splatty. Not from the front to the back. We want to see you. We want to see what you look like. You're making a fool of myself right now. Please come in front. Yes, thank you. This is Splatty, our co-host for today's. It's a small plushy toy, but it's going to help us learn about Gaussian splatting today. It's been created by just looking at a camera feed, recreating the 3D scene. We're going to see how to create one, how to use one, what the data looks like, how to implement one. It's going to be, all of our stuff is going to be based on Splatty. Don't look at me with those eyes, Splatty. Yes, you know what you're going to do with me today. Go closer. First question, what is splatting, Grandpa? Well, splatting's the easy part. We can think of paint splatters or throwing paint in a canvas. Well, that's the pretty easy part. We want to throw paint at something, big splats at first, and then progressively smaller splats until we get a picture or an image of something that works. But we do that with the technique that's called structure from motion. We take a couple of pictures at different angles and then realize the same cross patterns in this image and create a 3D mesh out of it. It's just a point cloud at first. But if we start, let's say, with a point cloud like that, and then throw, 7 million splats on this scene, we start to see the details. And if you refine the opacity of those splats with Gaussians, you get a very real representation of the original picture or the original video of what you're looking for, and then have a 3D scene that you can interact with very easily. So what is Gaussian, Grandpa? Pretty easy, too. It was devised by Carl Friedrich Gauss in the middle of the 18th and 19th century, probably in his pajamas, because he was a very brilliant mathematician doing so many things at the same time. But it looks complicated. It's not really. A Gaussian is like a bell curve or an exponential curve that you can parameterize to get the sigma or the length of it or the height of it. I'm not a mathematician. I don't know the right terms to describe that. But it helps you if you combine together multiple Gaussians in different dimensions. You get a zone, some place where you can get some information from. And then if you get a 3D Gaussian, you can probably get a good view of like a football or an ellipse in 3D in all the angles that you can have with a simple math that your CPU or GPU can really easily iterate on. Great. You also need something called adaptive densification. That is the place where you start with a small splat, and then you compare it with the original image and see it's too small, you need to clone it, and then the optimization continues to find the right angle and the right size of the splats to finally cover the space that you want. And then the other way around, if your first splat is too big, you need to overcorrect it, make it smaller or divide it, and then have the correct region represented in your thing. Cool. But then if you try to create a scene, you don't want to be static. You want to be able to move and have the camera angle change. So you need something called view-dependent color. It's done with spherical harmonics, very big names. But it's just a way to calculate a single point on a sphere and be able to represent it in simple mathematics terms. So depending on where you're looking at your splat, it's going to display a different color or a different gradient of color depending on what you've seen. So you can have very good representation of your scene. So this is it. 3D Gaussian Splatting for real-time radiance field. Here are our 4 friends because they're holding their SIGGRAPH 2023 Best Paper Award in August of last year. It's a very, very recent technical proposal, and it's very simple. That's why it caught up very quickly. Starting from the structure from motion points, you initialize your 3D Gaussians, just splat it, and then from the adaptation and view controls, you can iterate and in under 10,000 iterations, maybe, get a real representation of a 3D scenes. That's it. See, Grandpa, it's so easy. Any questions? No. I'm gonna move on. So what are today's goals? Well, learn about Gaussian splatting. That's done. Woo! 5 minutes. Learn about new C++ features. We're gonna go over that. And have fun, and I hope you're gonna all have fun and get out of here and say, oh, Gaussian splatting is so crazy good. How are we gonna do that, though? Well, if you know my style, I start from a real implementation, because I'm not the kind of guy that starts from zero and try to recreate the paper. It's too hard for me. I start from a real implementation that works, and then rewrite it in C++ and have it as a pretext to learn new techniques and new ways to learn about programming. And then make a presentation, because then I need a hard deadline to be able to, okay, I need to set my goals, and then, oh, I need to make it good to have fun. The reference implementation that I found, I need to thank Kevin Kwok on Antimatter 15 on GitHub. I just searched for 3D Gaussian splatting, and I didn't want it to be too big or too small, because I didn't want to have to redo libraries. I wanted to have like a full set of features, but not too many. And the code fits in a slide. Okay, maybe not. I'm going to zoom it a little so we can see it. There's a camera. Oh, yeah, there's a camera. With the ordinary thing that you would see in a camera, a position, a height, rotation, quaternion, or yaw pitch roll, a field of view width and height, and a couple of functions to use your view matrix. A view matrix is a 4x4 matrix, probably if you work in the game industry or in the recreation industry. I don't know. You've seen view matrix, and it's your bread and butter, but it's not mine, so I didn't know what to do with that first. It's just functions with a lot of calculations in them, but nothing very out of the ordinary. There are matrix transformations for, let's say, if you want to move your camera, if you want to pan, rotate, translate, things like that. It's not necessarily pretty, but it was like, it's JavaScript, and I didn't want to write it in C++. It's almost like C++ code. There's like those triple dot A slice that are not necessarily notation that we would see in C++, because they just expand A for the first 12 position and then do the other stuff. Okay, but that's easy to just write it in one batch. There was a worker, because the web worker tried to thread like the processing of the Gaussian splats. We're not going to see it right now. We're going to see it in the C++ implementation. Obviously, some OpenGL code to be able to render in a vertex shader and the other kind of shader, the fragment shader code, thank you, which are just like simple programs that you're going to send to the GPU. And then the main execution loop of the JavaScript code that we're not going to see, because it was just like parsing an input, like a path, and then just starting a Canva with OpenGL. Cool. The story began in December of this year. And what's crazy is that he started working on it in September, just a month after the paper was done. And then in November, I noticed this implementation, and in December, I started to work on it. So today we've seen a talk about the shoulders that we've built upon. It's exactly that. It's what small steps that inspires someone to do something else that inspires somebody else, and then I just found it crazy. So at first, I just removed all the controls specific to the JavaScript or the web platform, and then needed some basis, because I don't like to work from nothing. So I used a cute example. It was an OpenGL ES example to just load the logo and then draw it with OpenGL. It was super simple. The OpenGL window example isn't cute, so you need a QObject macro to make the signal and the functions work. That's not a problem. There's only 3 functions: initialize, resize, and paint the OpenGL code. So it's going to be pretty easy to replace with the JavaScript code inside of those functions. And then the data part that were there is a texture to represent your program, a VBO, a buffer object, array object. I don't know what those meant, but I just slowly researched my way. And finally, a logo to load. And the projection matrix, because, I could understand that, the words are the same in the same implementation. So it must be something, a world, an eye, and a target. So you're like your camera. Good. The first function in C++ that I translated, woo! It's not necessarily the most pretty one. Get projection matrix. Just changed everything to floats and then returned the vector and not much else. That's pretty boring. But the first choices came when I looked at the data. Because in JavaScript, there are special things that you can create, like a 32-bit int buffer array, but then pass this data to an 8-int buffer array and a float array, and then it's just going to work. Okay. In C++, I didn't want to bother, so I just created 3 different types of data with different sizes, and then just plug the data in 3 different places, because I didn't know beforehand why would they use sometimes float and sometimes chars and sometimes ints for the same kind of data. So that's an answer that we're going to have to learn. First thing that I learned, reading the data of this thing. It's just a ply file, the same type of file that you would see with laser scanners, just seems like a small point cloud. So you just try and read it with the file system. You want a vector of unsigned chars, because while I was debugging, looking at the data, it was needing unsigned chars. So your usual IF stream to read needs a reinterpret cast. And I don't like casts in my code. There's always a pain point. Why do I need a cast? I just need unsigned chars. Anyone knows how to read unsigned chars with an IF stream? No? Yes. There's a basic IF stream. What is an IF stream? It's a basic IF stream of a char. If you just redefine it as an unsigned char, you can directly read an unsigned char. Woo! It worked directly in MSVC. I know that maybe Clang or GCC needs a little more template parameters to there, but yeah, that worked. So no more casts. Woo! I can read the file directly. That was cool. But then it got weirder when I got into the OpenGL code. It's weird because it's full of macros and full of unknowns that you need to call the functions in the right order. So you bind a buffer to something to get the vertex and the triangles with a certain size. And then for the positions, you need to keep a string of the name of a variable to get the position, and then rebind the buffer right in the middle there. I'm not even sure it's correct code, but that was the code that I copied from the example that was working. So I was like, okay, I'm going to just follow along. But while trying to debug OpenGL code, you have to open the debugger, and then you have a whole bunch of errors generated if you, I just had my example from Qt at the same time as my other examples to see if I was doing something incorrect. I'll zoom on those examples there. What kind of error message? Poor people working in the 3D industry. Invalid VAO, VBO pointer used at high severity. High severity? Will I melt my GPU? Will I do something and explode my computer? Uniform is not an array, but count with brackets is greater than 1. Uniform is not an array, but count is greater than 1 without brackets. What's the difference? And then only every iteration, the same error. Array object is not active, high severity. Uniform is not an array, but count is greater than 1. And for days and days and days, the only thing that I had when I asked the code was, uniform is not an array, but count is greater than 1. Array object is not active, high severity. Uniform is not an array, but count is greater than 1. Object is like, But finally, I got to first light. My little Nike shoe that no, it's not mine. It was already splatted. But I was completely amazed because I can, come here. I can zoom on it, we can move it. That's the easy part. But notice when we can see the texture of the linen on top of this shoe there. We can see all the little details. We can see the transparency, because it's not transparency. It's just material or not material. Move. Thank you. I can prove to you that it's not a mesh. It's a real 3D model. I can go inside this shoe and show you the exact texture of that little part there that has been splatted. And it's not with professional hardware. It was just with an iPhone, just going over this shoe, and then you get a cool model. But that's not true. The real first light was more looking like that because there were still a lot of OpenGL errors about buffer size and then types. But I finally got it on the second time. Okay, maybe not. Maybe by the third time. Okay, maybe not on the first time. Okay, let's move on. But the code has been splatted. I just copy-pasted it on the top of the header file. I just wanted it to work. I tried to be clever and say, oh, okay, I'm going to create structs for those position, rotation, camera stuff that I may be going to need. No, I'm not going to need those. I'm going to remove them later. All I needed was the XYZ position of the camera and the field of view, FY and FX. But anyway, I didn't know then. Initialized it with structured bindings. That was cool. And then it's just the same code that you've seen in JavaScript, but in C++ now, without good formatting. It's the same functions that they were there, the same names, the same types that I tried to, okay, they get a vector in, they get the vector out, modified it, but yeah, okay. I just kept it the same way, kept the same window that I had, but needed to add just some functions to set the texture data into the OpenGL stuff, set the depth index that we're going to see later, and then recreate the worker thread, but not threaded, just the worker stuff that needed to generate the texture, run a sort function to sort the splats, because that's very interesting, and then just set the view for the display. The private part, I kept the texture, shader array, shader program. That's the typical stuff that you need to get it, and a bunch of functions and variables that I didn't need to know if it was working or not, because I didn't refactor first. But what do I do now that I have a functioning program that can display splats? Module it, of course. I'm a lover of C++ modules since 2020. And since CMake included it in their suite, I'm using it daily. So to do that in CMake list, I always put my modules in a separate library and just say, okay, all of those code inside of that library is going to be modules. I chose the IXX extension, but you can choose a couple of different ones depending on your compiler, and then link that library to my Splatty program. There's no magic in there. It's just a module. What does a module look like for people that have never seen it? Once you see a file with module at the top, it is a module. That's it. And then underneath, you export a module with a name. This one is going to be Splatty. And if I want to use this module, I just say import Splatty. It's just important that I import it after all my ordinary, old-style, boring includes, if I don't want to have problem with macro expansion and stuff like that. But it's just, okay, I accept that for the moment that we're not fully module support. That's great. But from one big module, oh yeah, that's okay. No. One module, one big one. I copied everything from the header file to a module, and then notice that I put the import first, the include first, and then just added export in front of all the functions that I need to export. And if I say export in front of a struct, everything inside the struct will be exported and will be available to use by the people that consume your module. So I didn't want to start with trying to get the dependencies out, just everything into the module and compile it. And then you see if it works or not. And it did. It wasn't so bad. But from one big module, that's not really the point of modules. It's to separate them one by one. So I kept my big Splatty module and then pushed the math function out, pushed the OpenGL code out in a module. Yeah, OpenGL code in a module, of course. The data that I need to use is in a module. The reader to read the data is in a module. The shaders to read the shaders are in a module. Oh no, you're not supposed to see that first. Multi-modular mastery, I called it, because yeah, you can, my big Splatty module now has a bunch of module imports. It imports what it needs to consume for the external mode, but most, I don't need to like export the symbols of the things that I don't need to else of my Splatty. That now takes a unique pointer to a splat data and a unique pointer to the OpenGL. So my Splatty, it's just a controller, let's say, to get the data and then send it to the OpenGL part. So it's going to be easier to split. Inside of the constructor of a Splatty, it takes a path, read from file from a Splatty, from the Splat reader module, gets the data. Okay, you can get the size of that data and then make the structures that I needed for the rest of the functions. The setView function, we'll see it a couple of times today, just an XYZ. We calculate a dot product of the view that we are right now and the previous view that we were. So we want to know whether we were like 10% farther than we were before so that we can recreate the texture and then resort those splats. Nothing else very weird in there. Yeah, and call the view change so that the OpenGL just as fast as possible re-renders your scene. And what about the other modules? The OpenGL module. I'm sure you're all aware that OpenGL code is ugly, but it's not as ugly as it is when it's all in a module. So I just set the view matrix there and all the stuff that was needed for the OpenGL stuff, like the texture type and things like that. The texture, the program, everything went in the module there. There's no limitations in what you can put in a module in this case. The different variables needed for the position, for the matrix, and the different functions for the OpenGL stuff. Is my timing good? Yeah. The view change function, I didn't do much, I didn't change it. The initialize GL. This is where you add shader from source code. So you have your shader source code, which was like just a string of a program that you're going to send to the GPU. Did it? Okay. You bind that program, you create your buffer array, you bind a bunch of stuff, you call you need to keep the positions of the stuff that you're going to put on your GPU, because there's like a way to process the data to the GPU back from the CPU. But most of it was just a trial and error of just, once I had those big OpenGL errors, just remove the code until I don't see the error anymore, and then re-put it back and just try and change the different variables and values, because I was looking at the documentation of OpenGL. It was not really helpful to say, what kind of macro am I supposed to put in there? But there, you put the texture data, a pointer to your texture data somewhere, so that I knew, okay, that's going to be where my data is going to be put in. So step by step, I could get to there. And then only the set depth index, because there's a depth table that we're going to see next, and the resize function that is not necessarily helpful because it just changes the way the view is set. So the shader modules is real interesting because it's nothing in there. It's just the two strings that I need for my vertex shader and my fragment shader. Remember that it's pretty ugly to look at because it's just a big string. If you want to modify that, you would have to modify the little main function there and the way you use the texture. I didn't try to modify anything in this code because it was cryptic for me, but I knew that if I reused the exact same OpenGL code from the implementation, it would work. But poor people that need to work with 3D graphics, that need to try that into the file exterior to that and then try and copy paste it into your source code to rebuild it. How do you do it? It's going to be quite cumbersome. The fragment shader is the same thing, but it manipulates the color of each pixels in your scene. But that's not what we want to see. Because every time you want to recompile something and try and debug it, it's going to be hard and cumbersome to move it back and forth. What we really want here is embed. Embed is a proposal for the next C++ standard in 26. We're hopefully going to have it. It's been decades that I've been a programmer. Yeah, decades. And that I've always wanted, and I will always needed to have a resource file into my executable to build it. With embed, that's exactly what it's going to do. You can have your vertex shader or your fragment shader in a file, use it in an external OpenGL IDE, that's great. And then once you save it, CMake knows that you've made a modification to the file that you're using, and it's going to recompile and relink just the thing that it uses at compile time. Woo! But this is not possible right now. The implementation didn't work for Windows, so there are implementations on GitHub that work. Battery has one that works cross-platform because it uses CMake magic to prepare the file first and then embed it. But This works in a module, const expert, embedded, shader, vertex, and fragment shader. Done. People like that? Yay. I tried to embed everything. I went crazy. I tried to, I tried to embed the data of a Gaussian splat. This file, plush, is 280,000 splats. It's only 8 megabytes. It's not supposed to be so hard to process, but yeah, no. You get an out-of-memory error pretty quickly from your compiler. My poor 32 gigabytes just exploded. They say that they're trying for the reference implementation to limit the size of what it needs to compile it, but I don't understand why an 8 megabyte file became a 32 gigabyte RAM compiling thing. But no, moving on. But it's promising. We're going to really have something great to embed stuff in our executables. Next. Water break. Because I'm going a little too fast, but that's cool. We're going to have more time for the end. What I really hate about a program is loops, of course. When you see a for loop, you see, it's tedious to maintain an index, stuff like that. So first of all, there's a lot of scalings. It's a matrix. You want to scale it. Sometimes you want the code to be as small as possible, as quick as possible. But in this case, the m variable is a 9-length table. And the scale is a 3-length table because it's only x, y, z, and you scale it maybe on all your positions there. OK, great. But then you need to find the right index for your scale because you only have 3 values and the other one has 9 values. You cannot vectorize that. I don't know how the compiler is going to do, but it's not going to be doing good code. There's a division there. But if the scale is the exact same size as m, just repeat 3 times the same values there. You can use a transform. There's a transform for 2 separate vectors, and then call multiply on them, and then they multiply. OK, you could have used zip. You could have used a couple of different stuff. But yeah, a small transform, it's great. Trying to optimize for space can lead to drawbacks for efficiency. Some more involved ranges transform, the counting sort that there's inside of there. Because you're trying to count your projection where you're looking at. You just want to draw the splats that the camera is going to be able to view. So you sort them by the view of the camera. So you get here it's a 16-bit depth sort. So it just sorts the 65,000 most visible splats. And to do that, it has to, in a single pass, count all the occurrences of the values it finds in the first table. Let's see that in a graph there. So it goes over each values, and in the other table there just keeps track of how many values with 1, how many with 2, how many with 3 there were. And then you get a table of your sorted splats in one pass. You don't have to go over there. If you pass only the index table to OpenGL, you can have already sorted array of which splat you want to use just by then taking the values that are the 65,000 most close to your camera. So that's pretty efficient. But there's a problem trying to modify that into ranges. It's quite complicated if you try doing one batch. So my test here was to remove the part of the function that was only touching one table at a time, the counting thing. So as a function, I could recall it in the same for and say, OK, count my depth, please, and put it into my depth array there. So then I could use a transform on this and remove the loop. And since it's a transform with only one parameter, you can use a view, depth views, transform, using the count lambda now that I've called, and use ranges to change it back to a vector inside my depth. So now, in one pass, I get my counting sort. Woo. And more fun with views is when you have those kind of stuff there. It's a big for with a lot of stuff to generate your texture. And the thing that always happens when you have multi-dimensional data in a vector, you need to stride it. You need to find the right index for the right place and then use your supermem copy to do that. But I didn't like it. I wanted to try and find a way to represent this algorithm with views. So I learned about views iota and views stride so that I get the correct index for my buffer and not have to calculate it every time like a times I. So now I optimized it. There's much less calculations going on. This particular for took 120 microseconds to operate. With the stride, it took 90 microseconds to operate, almost a 30% decrease, because I'm not doing calculations every time. I'm just always at the right spot in my buffer. Great. So it enabled me to understand more of my splats. So from the first splat, we can see the progressive display of those splats. And one by one, like a painter, it starts from the back because they're all sorted. And it paints the general picture of my Splatty. Okay, we don't have all day for the 200,000-ish splats. I'm going to speed it up by a factor of 30. But you're going to see slowly the features appearing. And the way the algorithm works is that it is sorted for the camera. You're going to see that a bunch of splats are aligned to each other because they're aligned to the view that they're looking at. At the beginning, I talked about view-dependent spherical harmonics. This doesn't implement spherical harmonics because there were too many variable points that the reference implementation said. Here it's only 32 bytes per splat instead of like 132 bytes per splat to have the spherical harmonics. But even if you don't have that, you still have very cool looking picture of a 3D model. Yeah. Can do it also with the little Nike shoes, so we can see how the algorithm chose to like create those splats and align them along the lines of thousands and thousands of iterations to reproduce the original implementation of this view. And then get the more detail every pass there. That's cool. Oh, yeah, of course there are casts in there because at the beginning you saw that there were a big 32-bit int casted back to an 8-bit and then to a float. A bit cast is new, I think, in C++20 or 17, I don't remember. But it's a safe way to cast something of the same size. So it's going to tell you if you don't put it at the right place. And then you can then use views transform to there. Funny thing, here I want a new buffer of float. Of unsigned in from my buffer of float. So I need to assign it to a new buffer. I didn't even know that would work into views because I'm used to like modify the view with a transform. And now it knows that since there's assignment, I want it to be converted, to be sent to my new buffer there. Cool, no more loops. Woo. With the data structure there, well, you have vectors. But okay, the world interaction would be moving the camera. I don't know, they invert the view for some reason, and then you can rotate it, translate it, or like use your keyboard and like add the code there to like interact with the world if you want a mouse or a keyboard or things like that. Then revert your view and can send it to the GPU. But playing with vectors is a little cumbersome because you need to know the indices of where you're looking at. I think you know where I'm going to. I started just converting all the vectors to an array because I knew the size of it, but that's not where I want to go. I want to go the mdspan way. mdspan new in C++20, but more implemented like recently. So this year when I did that, I didn't need to use any other implementation than include mdspan. MSVC has already shipped it in the latest Visual Studios. Great. So with mdspan, the cool thing is that you can use it really as a matrix, a 4x4 matrix. Here we don't see the benefits of changing it, but here, let's say the translate function. You get a bunch of indices, A, that you want to multiply to get your translation function. But with a matrix, what you're going to see is that you're going to use the extents or the dimensions of your mdspan to work with you. But the reality isn't always so simple. Right now, there is no context per operator bracket. It exists in the standard, but it's not yet implemented in Visual Studio, so you need to create a context per array of where you want to go to. But for me, it's a okay compromise for the moment, because now I can see where in my table I'm going to work. So std array and mdspan went everywhere in the code. To have something vectorized, you need to have it in a buffer inlined. But if you want to move it and use it as a multidimensional data, the mdspan is there for you. Even if you want to pass that mdspan directly to the OpenGL, there's a data handle function to like get the raw pointer out of this mdspan and then pass it to old style C functions if you need to. But the mdspan works. That's good. A good way to represent why is it better to use an mdspan to pass values everywhere. So this 2, 6, and 10, who knows what this is? Oh, it's written there. X, Y, and Z into a view matrix. Their position is fixed there. The 2, 6, and 10, it's for forward progression motion. You just got to remember it. But in an mdspan, you get a better view of where in that place it is, but it's still cumbersome. Okay, no, it's an std array of some places. But since it's a variable, std array, you can put it in the variable somewhere. It can text per variable and reuse it everywhere in your code. That's what we do, create code to be able to reuse code everywhere. So then your x, y, z position in your table becomes more elegant. You don't see that it's a multi-dimensional array necessarily. You just want the x, y, z position in your view matrix, and then you have it. Like that? What's the next part of it? Yeah, let's use a bigger file. A bigger file, yeah, a bigger file. Let's see, like, that's 2 million splats. Nah, there's a problem with there. We can see that we're in a train place somewhere, but now the splats are, maybe it's somewhere else in the scene that we can see that, no, there's a real problem. What you're supposed to see is that. I reloaded the original implementation with the original file, and it's much more impressive to see this train there. So I came back to original implementation, and what I did? Well, the first time that I tried to understand the code, I've put console logs everywhere in the code and see where the code path was going to. Everywhere it was not going to, I deleted the code. When I was looking at that, I said, oh, there's a part about the data processing that depending on the file type it's reading, it's going to do something else with the splats. Oops. So it works with smaller files because it's smaller functions. But when you get into millions of splats, then you need to compress them because you don't need all this quality information from everywhere. Or if you have this spherical harmonics into the splats, my viewer just removed them. I didn't know that because I did. Okay. Back to Splatty. Whee! We want to make our own splats. Someone asked the question, how do you do that? It's so complicated. The first splat that I created myself using Luma Labs was my brilliant keyboard. Yes, this same one here, our programmer's tool that we all use every day. It was super simple. I'm trying to not mess up. A simple 5-second video of me just going over my keyboard, and you can see the depth of the individual keys. You can see the use on my E key that is more used than anything else. And of course, the texture of the table without any more information than just a reference picture there. That is crazy. Even if you don't have good camera skills, because this is the real video that I use to upload this to Luma Labs. It does all the Gaussian splatting, and then you can just download the Gaussian splat file at the end. It doesn't need anything better quality than that. It can be shaky. It's just fine. It's going to find its way there. So you want to see good splats where they look like and get some pretty good results. I just ran into my garden and just recorded everything, trying to see, what it would look like. So the trees, the grass, the texture of the flower. What amazes me the most is the color. It can get the almost perfect color of what it was in the video in any angles. And the shadowings and the lighting. No ray tracing there. Oh, yeah. The best part is the tree. I just ran over my tree with a 10-second video, and it can infer the depth of all the leaves, the color, the shadowing of the leaves. You can go inside the tree and look at each individual branches. And using professional quality equipment would probably have professional quality results. With just my little iPhone 7 or 8, I have an old phone, can get really impressive results just from the amount of information that it can create, that it can infer from all those different views. Generate those splats, and then just iterate until it gets the view closer and closer to the reality. You can iterate indefinitely to get really to a pixel perfect precision. But I didn't stop there, sorry. I just need to. I just ran over to another spot in my garden where you have like places to grow food, but I wanted to see if it could understand the transparency of my goalie net here. And it doesn't understand anything. It just recreates the scene that it's looking at, the video that you've taken, the information from the texture of all the individual grass leaves that I don't need to recreate. So someone asked me, why would you use it in a game setting? If I want to play a Mortal Kombat game with my kids in my backyard, I could just Gaussian splat all of my backyard, and then here you have my real looking level for my Mortal Kombat game with my kids. Back to Splatty, yeah. Whee! I hope you like the talk since now, because now it's the part that I like about the talk. Because last year at this 2023 CppNorth, my new friend Andreas Fertig gave us a talk about coroutine for beginners. And then my mind was opened. For me, it was really a revelation. I just ran to everyone and said, hey, I'm exactly like Neo. I know coroutines. Coroutines? Yeah, show me. Great, great, great. I'll show you. A coroutine in a module. Yes, of course, in a module. I don't do anything else. The only thing you need to have a coroutine is two things. A struct, that is your coroutine type, and then you want to use this type, you create a function to define what you're going to do inside this coroutine. It's super, super, super simple. There are many customization points that make it look complicated. For me, when I look at an iterator class, I think it's complicated. Inside this coroutine, I decided to have a little fun. I just copy-pasted the chat examples. Where is my timing? How much time do I have left? I think I'm good. Oh, I have the time there. Great, I have 15 minutes. Good. I want to have a little more fun. I copied the chat examples that he showed me, that he showed us last year, and I wanted to have a little fun. So I start with fun level 0, and then co-yield a message. Hello, the fun can start. And while the fun level is going to be under 50, because when I play a game of Marco Polo, at some point it gets really annoying, someone saying, Marco Polo, Marco Polo, Marco Polo, stop that. By 50, it doesn't get fun anymore, so I return my coroutine and it's not fun anymore. So what's happening here? So every pass there, co-yield, it's going to stop the execution of my coroutine and then return the value to my original program. Then, if it's resumed, it's going to go to co-await, where it's going to wait for a data point to get inside this coroutine, and then I can put in the variable or something. Now I just printed the fun level and the message that I'm going to receive into my coroutine, and then I shout back Polo with the amount of fun level that we have left until the father said, get out of the pool, and then return. That's it. A coroutine is so simple. To use this coroutine then into my code there, I just implemented a hidden game of Marco Polo. So the fun starts, and then I created a function that is shout Marco. And somewhere else in the code, you just need to put the listen function to listen to, oh, you're supposed to hear Polo sometime in this pool game. So what it looked like, hello, the fun can start. Marco, Polo, Marco, 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 Polo, Marco, 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 Polo, Marco, 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 Polo. Get out of the pool, fun's over. That's not so complicated. The type of the coroutine is where the grunt work is done. What do you want to do with this coroutine? The promise type is a requirement. You need to implement a promise type. Okay, but inside this promise type, you can do whatever you want. Here we want to store the messages, which message we receive and which message we're going to send back to this coroutine. The little part that is hard to understand sometimes is those kinds of functions. Get return object, just the function that is going to be called when you call the initial creation of the coroutine. Initial suspend and final suspend, it's just what is happening when you get to co-yield. Do you want it to stop the execution or you just want to continue the execution of your coroutine all the way through? The good stuff, when it clicked into my head, what is a coroutine and what it does is when you say co-yield, it just calls yield value from this promise type. And then you say what you want to do. Okay, now from co-yield, I'm going to receive a message, store it into the message out value. When I see a co-return, it just calls the return value function into my promise type. And when I see a co-await, well, it's a little more complicated. It calls await transform functions with a bunch of stuff there that I've hidden, but the important part is when you call co-await, there's a move, your message that you want to receive into the coroutine. Not so bad. And there's, of course, a handle to this coroutine to be able to create functions inside this type. The shout function that you've seen, you want to shout a message. So you take the string and hold it into your promise of the coroutine handle, and then if your coroutine is not done, resume it, because now the value is inside the promise. It's going to be handed down to the coroutine. Same thing for the listen function, but it's the opposite. Listen is just, okay, listen, I'm going to resume the coroutine, and then when it's finished, I'm going to move the data that it's stored into the message out. Message out was the co-yield. When it yields a value, it stores it into the promise so that I can use it into my listen function. That's it. We can use more useful coroutines. So from the Marco Polo coroutine, I created like a little logging coroutine so that I could get a count somewhere and then a clock to be able to get my where am I in the code. I always put my co-yield at the top there. I initialize everything that I need for my coroutine and then stop it there. And then co-yield something, because I like it. It creates a coroutine, initialize all the memory that it's going to need, and then, okay, pass it to the other people. While C++ is under 100 years old, I just want to have a slide with C++ on it. Co-yield the time or the duration cast of where you are now. So you have a count and a timing. And then finished while it's underneath. Because usually when I log something, I don't want it to log for the whole lifetime of my program. Maybe it's just at the beginning when I'm loading the file. Maybe it's just when the user interacts with the view, something like that. Now, this one was just to count where was I, because every time that I passed this code in, I was at the exact same time, at the exact same count. But here you see that it took 2 seconds to get to my 98th count. If I optimize the code, I'm going to always get to the same value, but maybe faster than 2 seconds, because it's going to iterate faster or slower. So then I can see that, okay, my code is getting better, but what's happening if I change from a vector to an array to an mdspan? Does it change the timing? So once I had this little counting logger, I could be comfortable with my changes, that it wouldn't affect the performance. And it wouldn't affect the performance for the whole lifetime of the program, just for the amount of time that I wanted to log. That's cool. But the serious coroutine, that was just toys, right? That was just playful. The generate texture coroutine, it's a little bit more involved, but it's not really complicated. It's just, it takes the texture data, it waits for the data to enter the coroutine. So it initializes the coroutine, waits for its data to go there. And while the world's still running, for every splats, we copy the position, the color, the matrix product, blah, 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 set it in the texture data, and then yield the texture data. So we got a texture generator now. Cool. The promise type now keeps 2 values. What it needs to produce is the texture data, and what it needs, what it produces, what it needs to produce, the splat data. Inside of the promise type, in my yield value and my awaiter, it's the same thing. I just wait for a value to come in, store it, or once the value is ready, store it for the people to use it in my promise. Nothing really weird in there. And the functions that I used to interact with my coroutine was just to set data and texture to retrieve the texture value here. You see that there's no coroutine thing there. It's just get the texture out, get the texture out. It's a read value. It doesn't change anything. It's thread safe. And if I want to regenerate my texture, I split it, and I just need to call the resume function to just create me, and then I don't need to tell me when you're ready. Just generate the texture. I'm going to just continuously read the texture. So after I've put my texture coroutine inside, I just had to put the generate texture and then read back the texture there, because this is all done sequentially. Woo! But during a late night debugging session, because most of this stuff has been done during a late night debugging session, I've seen that my Splatty was pretty laggy with the coroutine. It's like, I've implemented the coroutine. I thought this code was supposed to be asynchronous. I thought it would be naively be run in parallel, but it really doesn't. It doesn't at all. It's asynchronous. It's one at the time. You just pass the ball along. But I really wanted it to be in parallel and asynchronous. So every time I called this resume function, it would block. It would just resume the coroutine. And then once it was done, after the closing bracket, then the stack comes back to my main program. OK. Naively, I just threw a JThread to there. It's like, OK, I just want to run this resume function in the JThread. But the problem with this didn't work well. Oh, the animation doesn't start there. Anyway, didn't work well. Because why? Because the JThread joins immediately after the closing bracket, so it did exactly the same thing. It was blocking anyway. So if I want a thread that is not blocking, and I'm just very tired and I want to get it done, I just put a thread into the coroutine structure, and then created one when I needed it, and if it's not joinable, just move it into my thread and resume. So this works. This resumed my... No. It's supposed to be moving out by itself. Ah, boo. So, we won't even see the before and after. That's was the most important part. Why? Just a shame. Maybe if I do it manually. Not even if I do it manually. Someone corrupted my video. Anyway, it was, I saved my file yesterday and I shouldn't have modified it. Anyway, it was moving smoothly. Please trust me, it was a little better. But it was not necessarily perfect because the problem was not the generate texture function. Generate texture was supposed to be done once in the constructor because the texture didn't change. It was the sort function that was sorting all the time that I should have put into a coroutine. But that's going to be for the next time because I don't have any more time anymore. The Eureka moments were full into the creation of this. Rewriting the tutorial from C++ to OpenGL was really hard but really rewarding. The surprise STD embed, I really like that we're really close to having an embed into the standard. Converting fors to ranges was very difficult. Took me about maybe a month of just trying, but there's still for loops inside. But there's a bunch of them that has been converted to algorithms. Native mdspan makes your multi-dimensional tables work better. Coroutines, of course, were the big new part for me, learning coroutines. And then every time I see people saying that the coroutines are too complicated or too heavy, no, just copy an example that works and then work your way through. That usually works. And if you want to do threading in coroutines, don't do what I've done because it's probably not safe at all and very weird, but it fitted what I wanted to do. So I have a time for a recap of the code. And yeah, this is exactly the code that runs on GitHub. Nothing's hidden. I know it's very small, so that's why I'm going to use the magnifying glass to try and show you the main. I really like main functions to be as simple as possible with nothing in them anymore. You cannot put a main into a module. This is the only limitation. It has to be in its own file there. Is it big enough? Yeah. Into the OpenGL window, there's nothing special about it because it's just import the Splatty and then go on with your life. Into the CPP, the paint just sets the view, recreate the world interaction, sets the view and update the Canva. And then the update world interaction. I've hidden here, I have a special branch just for the controls where I was using the keyboard, where I was using the mouse because I just copied the code from the OpenGL, the JavaScript implementation. The Splatty is not much more complicated than it was before, but you see that we copy the buffer and then using our little ranges to copy it from a float buffer to a UID buffer. The reader that read the file that we've seen the basic IF stream to read a file into the module. Yeah, of course, you put all the old include files into the global module fragment at the top there. And then everything underneath is going to be into your module. You can export a namespace, and everything into the namespace is going to be exported. Cool. And the shaders with the embed, obviously. What you probably want to see is the real coroutine code. Yeah. You're going to see it. Oh, no, that's the real coroutine code. So the count logger, oh, I cannot zoom better than that, was just the same promise type with the log message that was inside of it with the little specification point for what you do when you yield a value, when you return a value, or the awaiter object that use the call wait. The texture generation, which does the same thing, which keeps the texture data and the splat data inside of it. Yeah, I'm going to be fine. And then weird promise type pointer castings and stuff like that. Yeah, just copy the examples and it's going to work. Set the data, generate my texture with my, if my thread is not joinable, create a new thread and resume it. Eee! Where's the join? Yeah, and the destructor there? Yeah, don't do that. I guess it's just going to create one thread and just do it once. Because then I understood that, okay, I just need to generate the texture once. But for the sorting would be good. And then inside of Splatty, there's nothing really left here. Don't need to make a big announcement. Oh, that's the OpenGL one first. Yeah, but the OpenGL is not really interesting to see because it's just calls to OpenGL, functions, variables, bah. The Splatty code, I kept it very ugly because I wanted to show that there's a lot of math going on. Oh no, that's the math module. And the Splatty module that integrates all of them at the end. Takes the coroutine, the data, the OpenGL, the math. I selectively chosen to put the coroutine definition inside of my Splatty file because you don't need to put it close to the coroutine type because you can create different coroutine definitions with the same type. I could have created different kinds of logger using the same type of logger or different types of coroutine texture generation with the same type of texture generator. That's why we have in the 23th standard an STD generator to have a coroutine type that just generates those types there. Cool. What a journey. It's been very fun, but it cannot end here without a real invitation to a barbecue. No! This one needs to work. This one needs to work. Oh yeah. Whew. The barbecue. I went to my beautiful Weber barbecue and just ran over it over and over and over with my camera to have a scene where we can have a sit. So once you're coming to Montreal the next time, you can go to my house and you can have a nice ribs or a nice barbecue with me close to my Gaussian splatted barbecue. But what's really cool about it is that it didn't catch the reflection right, but you can see a big black blob into this barbecue there. It's me moving with my camera. Depending on the view where it is, we can see me inside of it or close to it. Did it stop? No, okay. Oh, it's lagging now because it's getting hot. But you get a sense of what it's capable now. It's capable of recreating a 3D scene. Imagine if I had an autonomous vehicle here. It's not fake, it's real information that it can infer depth to it. And if I don't want a drone to bump into my tree, it gets the real information about the 3D depth of my tree and then could maybe fly around it. It doesn't need to have radar, it doesn't need to have anything, just have the real representation. I'm gonna zoom out a little bit so that you can see the whole scene of it. I didn't want to film the rest of the backyard there. I just wanted to film the Weber barbecue there in the middle. But we can still see that it can infer information from the rest of the scene there and from most of the rest of the backyard there. So let's say that I really wanted to have a perfect backyard. Every day I could just go inside of it, just film it, and just re-add to the same scene because the point cloud is going to be exactly in the same place. Yeah, that has been such a journey. It's been so cool. Thank you. That's all I got. Right on time. So if you have questions, I'm going to be hanging out with my Gaussian splatting energy. You can ask me and come visit anytime.